All right, let's talk about Coulomb's law. Now, before we talk about Coulomb's law, we have to talk about the electric field because Coulomb's law arises from the electric field. So the electric field, all charges produce a field that radiates outward. This is kind of like the force of gravity, right? Our gravitational field that is produced by the Earth. And we know that when we have objects within Earth's gravitational field, it is affected by the Earth's gravity. So when we have other charges within a charge's electric field, they are going to have a force put on them due to the electric field that they're in from another charge. So this field is proportional to the strength of the charge, which means that a larger magnitude of charge means a stronger field. And as we move away from the charge, the field gets weaker. Just like the gravitational field, right? When we move away from the Earth, the gravitational force gets weaker. Now we represent the electric field as lines coming out from or going into the charge. Those electric field lines point out of positive charges and in to negative charges. The density of the lines represents the magnitude of the charge, also represents just the strength of the field, right? We know that a charge with a larger magnitude means a stronger field. So the stronger the field, the denser the lines. Also, when you get closer to that charge, the lines will also be denser, meaning the closer you are to the charge, the stronger that electric field is. Here's some examples of an electric field line diagram. So we have a positive charge. Those electric field lines are going out of the positive charge. We have a negative charge, and the electric field lines are going into the negative charge. We can see that closer to the charge, we have closer together lines, which means that they're denser, which means that that field is stronger closer to that charge. As we move away from that charge, the lines spread out a little bit more, which means that the field is weaker as we move away from the charge. Now here's again our density of the line. So we can see that the charge on C is going to be the strongest because it has the densest lines, which means it has the strongest electric field. We can also have electric fields produced from two charges together or more. We can see, again, this electric field goes out of the positive charge and into the negative charge. Here we have two positive charges, so it almost creates an electric field of zero in the middle here. They kind of cancel each other out. Now, electric force is going to be what arises from that electric field. So when a charge is located in the electric field of another charge, it feels a force. Again, with our example, kind of analogy of the force of gravity, when there's an object within the Earth's gravitational field, it feels a force from the Earth's gravitational field. So that force, the electric force, is proportional to the magnitudes of the two charges and inversely proportional to the distance between them squared. The force between two opposite charges is attractive, so we know that a positive and a negative charge will attract one another, opposites attract. And the force between two similar charges, so a negative and a negative, or a positive and a positive, is repulsive, so they will repel one another. Now, Coulomb's law is what quantifies the amount of electric force that two charged objects exert on one another. So it is giving us a way to actually calculate the amount of force. This is the equation for Coulomb's law. Its force is equal to KQ1 times Q2 over R squared. Again, you've seen an equation very similar to this. And this K right here is a constant. It can also be part of the numerator, so you can see this just as KQQ over R squared. F is the force between charge 1 and charge 2. Q1 and Q2, these are the charges that are exerting forces on one another. Now, it can be either capital Q or a lowercase q. You will also see it as a lowercase q. It doesn't really matter whether you use a capital or a lowercase. Now, the reason that they have absolute values here is because we are basically finding the magnitude of the force, not the actual direction of the force. You will have to find the direction based on whether or not those charges are positive or negative, and if we are repelling or attracting. R is the distance between the charges. And then K is Coulomb's constant, which is 9 times 10 to the 9th newtons times meters squared per Coulomb squared. So here we know forces in newtons, distances in meters. Now this is a new unit, this capital C, that's our Coulomb. And that means that charge is in coulombs. Now charges usually are very, 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 very small. We're talking about, protons, electrons, things like that, and maybe a little bit more charge than that. But because charges are very, 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 very small, you'll sometimes see charges in like microcoulombs or nanocoulombs. All right, and those are just really, really small units of charge, just like millimeter, right? That's a small unit of measurement of length, but we can also have micro. So milli is a prefix, meaning 10 to the negative 3. Micro means 10 to the negative 6, and nano means 10 to the negative 9th. And I have it in my example next, so I'll show you what I mean by that. So here's our example. We have a force with a magnitude of 2.2 times 10 to the third newtons exists between a positive charge of 600 microcoulombs and a negative charge of negative 200 microcoulombs. What is the distance that separates the charges? So here's the micro example that I was talking about. Now, first and foremost, we have to talk about what this micro means. So a microcoulomb, and that micro is just kind of a fancy U/M, kind of thing. It's a Greek letter, of course, it's called mu. But a microcoulomb is equal to 1 times 10 to the negative 6 coulomb. So you can use that as a conversion factor. Now, there's an easy way to do this. If you get just 200 microcoulombs like that, or negative 200 microcoulombs is what we get, and 600 microcoulombs. I have charge 1 is equal to 600 microcoulombs. All I have to do is just add that times 10 to the negative 6 on there. So I get 600 times 10 to the negative 6 coulombs. Now, if you want to see how that actually works, what we get here is 600 microcoulombs, and then we use our conversion factor. In 1 microcoulomb, there is 1 times 10 to the negative 6 coulombs, all right? That microcoulomb is very, 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 very small. So that's why we get such a small number for our coulombs. So again, this just turns out to be 600 times 10 to the negative 6 coulombs, or if you do this in your calculator, you'll get 6 times 10 to the negative 4th coulombs. That's the same number, right? But 6 times 10 to the 4th to the negative 4th is more scientific notation accurate. So there's our first charge. Our second charge, Q2, is equal to a negative 200 microcoulombs, which is negative 200 times 10 to the negative 6 coulombs. And then we know that the force between the two is 2.2 times 10 to the third newtons. And then we want to know the distance that separates the two. So we want to know what R is. Okay, so we know that force is equal to K times Q1 times Q2 over R squared. Again, this is the other way that you can write this equation. It means the same exact thing, okay? Now, I want to know R, right? So what I can do here is I can actually solve this equation for R, or I can start plugging in my numbers. That's totally fine. But what I'm going to do is I'm going to solve the equation for R. I'm just going to cross multiply here. So I get F R squared equals K Q1 Q2. And then I'm going to divide by F. So I get R squared is equal to K Q1 times Q2 over force. And then we'll take the square root of both sides. So we get R is equal to the square root of K times Q1 times Q2 over force. So now what we can do is we can plug in our numbers. We get the square root of K, which I didn't give you on here, but remember, K is a constant, and I should write it down up here. K is equal to 9 times 10 to the 9th. Newtons times meters squared over coulombs squared. Okay, so we're going to plug that in here. 9 times 10 to the 9th times Q1, which we found to be 600 times 10 to the negative 6 coulombs, times Q2, which was a negative 200 times 10 to the negative 6. But we're just going to plug in a positive because what we're getting here is R. We don't want to have a negative number under the square root because that doesn't make sense, right? So that's why there was absolute values around those charges that I showed you when I introduced this Coulomb's law equation. And then we divide the whole thing by the force, which was 2.2 times 10 to the third newtons. All right, so doing this on my calculator, I'm going to put parentheses around everything on the numerator first. So open parenthesis, 9 times 10 to the ninth, close parenthesis, times, open parenthesis, 600 times 10 to the negative 6, close parenthesis, times, open parenthesis, 200 times 10 to the negative 6, close parenthesis. So I'm going to press enter here. So I get everything on the numerator first, which is 1080. And then I'm going to divide by, open parenthesis, 2.2 times 10 to the third, close parenthesis, and I get 0.49, and then I'm taking the square root of my answer, and I get 0.7 for my distance. And remember, this is in meters, so 0.7 meters is about 70 centimeters. So that's the distance between those two charges.